Section 19, Cosmic Microwave Background Variations and Baryon Acoustic Oscillations, BAO. This section was updated in February of 2025. The Cosmic Background Explorer, COBE, satellite in the early 1990s confirmed that the CMB signal from patches of the sky has a near-perfect blackbody spectrum corresponding to a temperature of around 2.7 Kelvin, slightly less than 1% of room temperature. The WMAP satellite in the 2000s had better accuracy and better angular resolution than COBE. This image is an artificially colorized representation of the blackbody temperatures of the microwave signal received from different directions of the galactic sky by WMAP. The average temperature across all directions is shown in green. Red is very slightly warmer than green. Blue is very slightly cooler than green. This ellipse represents the entire sky. The first image is all green. In any direction, the microwave signal matches a blackbody spectrum corresponding to a temperature, and the temperatures in different directions are all the same on this scale. This confirms an important assumption in cosmology, that the energy density of the universe is the same in all directions on the largest spatial scale. This is one of the assumptions required in order to use Friedmann's equations, which produce the scale factor versus time that we rely on. The second image has the contrast amplified by a factor of 1,000. The red area in the upper right and blue area in the lower left are due to a dipole Doppler shift due to our peculiar motion with respect to the universe, which astronomers can correct for. Earth is moving 30 kilometers per second in its orbit around the Sun. The Sun is moving 250 kilometers per second in its orbit around the Milky Way. The Milky Way and Andromeda are moving toward one another at 123 kilometers per second within our local group. Our local group is moving within the Virgo supercluster. The Sun's net motion is 370 kilometers per second with respect to the cosmic microwave background frame of reference, 1,000th of the speed of light. The third image has removed the peculiar motion Doppler shift and then amplified the contrast by another factor of 100. The red horizontal band across the middle is microwave emission from gas and dust in the Milky Way galactic plane. So this red is a contrast amplification of this red. The fourth image has this subtracted out. I have not learned how it was subtracted out. It's not just that they deleted the pixels, because we still see pixels in those places. Then the microwave background is thermal in every direction, but with temperature varying slightly, within 30 parts per million in different directions. Here are the highest resolution temperature results from the Planck satellite, with the Milky Way anomalies processed out. Planck is the scientist who discovered and developed the correct theory for blackbody radiation. The red regions represent slightly higher temperatures, and the blue regions slightly lower temperatures. A few large areas are slightly warmer, like this large area, or slightly cooler, like this cool area, than average. But there are also many more slightly warm and cool variations or fluctuations on every scale down to the limit of resolution of the Planck data. The average temperature is 2.7255 Kelvin. The fluctuations are within 30 parts per million. At CMB last scattering, our visible universe was uniform in temperature, energy density, and matter density to within 30 parts per million. We could stop here and skip to the next video, but the fluctuations help cosmologists model the composition of the universe and check their models. So let's go a little further. The CMB data has been analyzed for the temperature differences between all pairs of points in the sky as a function of the angle separating the pairs of points. For example, the dipole component is a strong difference for pairs of points in opposite directions, 180 degrees apart. But that signal gets removed from the analysis because it is solely due to our peculiar motion, not the density variations of the universe, and so we can see smaller signals. This graph is called the power spectrum of the CMB temperature fluctuations from the Planck data, and it tells cosmologists a lot about our universe, though it is complicated for us laymen, and I don't understand it fully. Nevertheless, I will present what cosmologists are saying because it's one of the few tools that cosmologists have for figuring out what the composition of our universe is. On the horizontal axis, each angular size, like 1 degree, corresponds to a particular physical size on the last scattering surface and a particular size presently. All this information comes from the last scattering time. The dot on the far lower right, Planck's limit of resolution, is a size then that now, due to expansion, is a few times larger than the size of galaxy clusters, but smaller than galaxy superclusters or cosmic voids. All the other dots are larger sizes, increasing in size from right to left. The size now of the region corresponding to the angular size of the third peak, 0.22 degrees, is about 55 megaparsecs, roughly comparable to a single galaxy supercluster or cosmic void. The size now of the region corresponding to the angular size of the highest peak, the first peak, 0.8 degrees, is about 200 megaparsecs, large enough to include both galaxy superclusters and cosmic voids. It turns out that the physical cause of the temperature fluctuations is different for large angular sizes than for small angular sizes. For angular sizes greater than 1.1 degrees, left of the vertical dashed blue line where I have my cursor on the power spectrum graph, the distance between the pairs of points at the last scattering time was larger than the particle horizon distance at that time, and those 2 points could not have been in causal contact since the extremely early universe, since the end of cosmic inflation. But small angular sizes, right of the dashed blue line, had been in causal contact for some period after the early universe, after cosmic inflation. This will be a little confusing for us, and I hate to present material that I don't fully understand, but nevertheless, I think there's value in hearing what the cosmologists are saying. For angular sizes greater than 1.1 degree, left of the vertical dashed blue line on the power spectrum graph, CMB cool spots are believed to have been slight overdensities of dark matter at that time. Photons lose energy escaping the gravitational well. And CMB warm spots are believed to have been slight underdensities of dark matter. There are fluctuations at all angular sizes, underdensities and overdensities at all angular sizes. For angles larger than 5 degrees, temperature and density fluctuations are low, but non-zero. But there is a lot of scatter in the data at large angles. The red dots are data, the green curve is model, and the red bars are a range of data. With the large scatter, there is opportunity for improvements in measurements and of cosmological models. There is a cosmological problem with uniformity on large scales, called the horizon problem, which we will cover later in the section on cosmic inflation. The European Space Agency website says, the green curve represents the best fit of the standard model of cosmology, currently the most widely accepted scenario for the origin and evolution of the universe, to the Planck data. The pale green area around the curve shows the predictions of all the variations of the standard model that best agree with the data. While the observations on small and medium angular scales agree extremely well with the model predictions, the fluctuations detected on large angular scales on the sky, between 90 degrees and 6 degrees, this lower left area of the graph, are about 10% weaker than the best fit of the standard model to Planck data. At angular scales larger than 6 degrees, there is one data point that falls well outside the range of allowed models. These anomalies in the cosmic microwave background pattern might challenge the very foundations of cosmology, suggesting that some aspects of the standard model of cosmology may need a rethink. On smaller angular sizes, less than 1.1 degrees, the temperature fluctuations are believed to be due to Baryon Acoustic Oscillations, BAO, and the data match the green curve very well. Baryon Acoustic Oscillations is a funny term. Let's learn a little about it. Before and after the epoch of recombination, cosmologists believe that cold dark matter, which then dominated expansion of the universe, had a pretty uniform density, but with small density variations on all scales. Overdensity regions expanded slightly slower than the universe's average expansion, so a relative contraction. and underdensity regions expanded slightly faster than the average expansion of the universe. The density variation magnitudes grew slowly since the first decades after the Big Bang, when radiation dominated expansion, and then faster once dark matter dominated expansion. Let's imagine a single small-sized dark matter overdensity region that will eventually become a galaxy supercluster. Where there was a local dark matter overdensity, there was a local gravitational attraction toward the center, and a local dip in the gravitational potential or gravitational well. Dark matter particles accelerated toward the center of the well. This left the surrounding region slightly underdense and increased the overdensity. Distances were large and speeds non-relativistic, so it took time for the overdensity and underdensity to increase in magnitude due to dark matter particles traveling in space, but the overdensity was also increasing in magnitude due to locally slower expansion rate. Given enough time, when dark matter particles reach the center of the overdensity gravitational well, they have their highest kinetic energy and velocity. Dark matter is unlike ordinary matter in that it appears not to interact with light, ordinary matter, or itself, other than through gravity, at least since the first 100 years after the Big Bang. Dark matter particles cannot collide with one another inelastically, cannot emit electromagnetic radiation, cannot shed kinetic energy, and cannot condense at the center of the gravitational well. Dark matter particles continue past the center to the other side of the well and would oscillate back and forth given enough time. But since the particles are in motion, not parked in their original location, a shell of underdensity develops surrounding the overdensity. The overdensity is broad and gentle, not highly contracted like a star. Protons, electrons, and light behave differently than dark matter particles. Prior to recombination and photon decoupling, the photons, electrons, and hydrogen protons, baryons, constitute a single coupled fluid, a plasma, whose energy density is only 40% that of dark matter. Photons don't get very far before they scatter off free electrons of the plasma. The universe is still opaque, optically thick. The photon-electron baryon fluid starts to flow toward dark matter overdensities, gravitational wells. And it would flow away from dark matter underdensities. This is a diagram only of an overdensity. However, as the fluid gets compressed by gravity, its temperature and radiation pressure rise with its density. The temperature and pressure cause the fluid to expand outward from the overdensity, to rebound. Dark matter particles do not rebound, so the gravitational well remains. Fluid expansion causes the temperature and radiation pressure to drop. Gravity then causes the fluid to flow inward again. This inward and outward cycle of the photon baryon fluid is called Baryon Acoustic Oscillations, BAO. This is important to cosmologists because it gives them important information about the composition and parameters of our universe. Details depend on the size and magnitude of the overdensity. I believe the process for underdensities is similar but slightly different. But then the universe's temperature falls to the point of recombination, decoupling, and last scattering. The universe becomes transparent for photons. Photons can now travel the universe unimpeded. If the fluid at some particular overdensity happens to be at maximum compression at the time of photon decoupling, the photon temperature for that particular overdensity will be slightly warmer than average, and the cosmic microwave background temperature will be warmer there. If the fluid at some other specific overdensity happens to be at maximum expansion at the time of photon decoupling, the photon temperature for that particular overdensity will be slightly cooler than average, and the cosmic microwave background temperature will be cooler there. The first peak, at angular size 0.8 degrees, is said to represent those dark matter density variations for which the photon baryon fluid was at maximum compression at the time of photon decoupling. I don't follow the details, but the angular size of the first peak, 0.8 degrees, tells cosmologists whether the curvature of our universe is flat, positive, or negative, and the data is consistent with zero curvature, flat, but it might just be small. The angular size of the first peak also helps tell the matter density versus dark energy density for our universe. The size now of the region corresponding to the angular size of the first peak is about 200 megaparsecs, large enough to include both galaxy superclusters and cosmic voids. The amplitude of the first peak tells cosmologists the number of photons per baryon, 1.6 billion photons per baryon, and the baryon density of our universe, 4.9% of the present energy density of our universe. The size now of the region corresponding to the angular size of the third peak is about 55 megaparsecs, roughly comparable to a single galaxy supercluster or cosmic void. Astronomers are looking for large rings corresponding to the BAO peaks. These images are an illustrative visualization, not actual data. The left image pair shows the CMB fluctuations due to the first peak on the left of the left image versus if there were no first peak on the right. You can see that the red and blue areas are more intense when there is a third peak. The right image pair shows the CMB fluctuations due to the third peak, this peak, on the left of the right image, versus if there were no third peak on the right. The peaks increase the magnitudes of the fluctuations on that angular size. Note that the peak is not a periodicity in space. It's more like a feature size. Here I would like to give a shout out to Ask Ethan and the Starts with a Bang articles on Big Think. His cosmology and physics articles are very helpful, and he makes amazing graphic images, such as this one. Independent from CMB variations, Baryon Acoustic Oscillations also create a measurable bump in what is called the correlation function of galaxies in space. This gives cosmologists a second measurement independent of the CMB variations. This measurement is used to improve their estimate of the matter versus dark energy content of the universe, and whether dark energy density is constant over time. The co-moving radius for the BAO bump is large enough to include both galaxy superclusters and cosmic voids. This graph shows possible energy densities of the universe as a fraction of the present critical energy density, with matter on the horizontal axis and dark energy on the vertical axis. So the lower left point would have matter energy density of 0.2 of the critical energy density and dark energy density 0.6 of the critical energy density. The area within the long light gray bubble is the 95% confidence level from the data from the CMB combined with Type 1a supernova data. The area within the black bubble is the 95% confidence level combining CMB, supernovae, and BAO peaks data. The dashed line represents zero curvature, a flat universe. From this processing of data, cosmologists believe that our universe, presumed to be the center of the black bubble, is 13.78 billion years old, flat, at critical density, with 68.9% dark energy density and 31.1% matter energy density presently, and that dark energy density has been constant with scale factor and time. The universe is either infinitely large or much, much larger than our observable universe. But cosmologists will continue to seek higher confidence levels from data. The data from CMB and BAO defines some of the parameters of cosmologists' standard cosmological model. You might also see the term concordance cosmology. I know that some of this material is confusing. I don't fully understand it. What we must realize is that cosmologists cannot simply measure the energy densities of dark matter and dark energy in the universe. They must use whatever indirect measurements they can, tested against the standard cosmological model. This is the end of our material on the CMB and BAO.